Hello, everyone, and welcome back to another exciting day of algebra. Today, what we're going to be doing is going over something called the sets of numbers. Before we get completely started, what I need you to do is go where you found this video. There's a worksheet, or not a worksheet, but notes. It should look like this, except it's already been, it's completely blank, and you're going to be filling it in as we go. So that's what I need you to find first. After that, come back to this video and take notes with me, and you're going to be keeping this in your binder for your future uses. So as I was saying, the largest set of numbers is called the real numbers. And we have a special symbol whenever we talk about it. And real numbers, real starts with R, so we usually use an R to denote whenever we're talking about it. Except it's called a double scripted R. So we basically have two lines going down as the backbone of the R, and then we just finish off writing R, if that makes any sense at all. So what this does is it gives you what the set is. So in this case, the double scripted R, and then it's going to tell you what those numbers look like. So the real numbers, well, they're all numbers. And I'm going to put a little asterisk here, and I'm going to say it's the real numbers, or all the numbers for right now. So for right now. Once you move on to Algebra 2, you're going to be talking about a different set of numbers that, well, if you have something that's real, you can also have something that's imaginary. So the other set of numbers is called the imaginary or complex, but we're not going to talk about those in this class pretty much at all. We might do about this much of it, but that's it. Then, if we have numbers like other than the real numbers, we can break them into two different categories. They're either irrational or rational. And the difference is, irrational are numbers like pi. Pi is irrational because its decimal just keeps on going. So if you search what are the decimals of pi, you can basically fill a terabyte or more worth of information on your computer just going through and listing each number that's after the decimal for pi. It's never ending, and it's never repeating, so it goes on infinitely. If we have numbers like that, we call them irrationals. So if we look on the left side of this worksheet, we have the irrational numbers, and irrational starts with I. So mathematicians who came long before me decided that a double scripted I is going to create the set for this. And then some examples we have would be pi. We also have the square root of 2. It's actually a very famous number, mostly because back in ancient Greece, there was a time where if you knew math, you were pretty much rich. And during that time, somebody named Pythagoras came around and created something that you probably know, the Pythagorean theorem. And that caused a huge uproar in the math community. And what actually happened was that somebody said, well, if you do this and that, it doesn't work because square root of 2 is irrational. Well, that causes Pythagoras to go and kill the guy by basically paddling him out into the middle of a lake and pushing him over and drowning him. So not only does math have like a dark history, it's interesting too. But that was square root of 2. Then we also have another one that's like negative square root of 101. It's also going to be an irrational number. But other than that, those are the examples I'm going to give you for irrationals. The other side of this would be the rational numbers. So all that a rational number means is that the decimals will eventually end, and they have a pattern to them. So like if you look at 2 over 3, so 2/3, its decimal is 0.6666666666666 repeating. So it just keeps on going forever, and its repetition is 6. That's one example that we could use. But before we go to that, the symbol that they chose for rational numbers. Well, rational starts with R, right? And you think it should probably be an R, but the real numbers are a double scripted R, so we don't want to do that. Instead, we can think of the rational numbers as a ratio, and another word for ratio is quotient. So instead, the rational numbers are written by a double scripted Q. So you draw a Q, and you just add a second line inside of the circle. Some examples of rational numbers would be, 2/3, like I just mentioned. We could also have 1/3. We could have the square root of 16. And of course, we can have negative 2/3 or negative 0.667. As long as the decimal ends and it's repeating, we can say that it's a rational number. Next, we have a slightly smaller group of numbers, and it's the integers. We should be pretty familiar with those. Basically, it's all of the negative numbers, or negative whole numbers, 0, and all the positive whole numbers. And somebody, I think the word came from Germany, they decided that the symbol for integers was going to be a Z. So we're going to have a double scripted Z. And again, I said that it's all of the negative whole numbers, 0, and all of the positive whole numbers. So that means that we go all the way to negative infinity. So I'm going to put those 3 dots, and inside of those 3 dots are all of the numbers except for -2, -1, 0, 1, and 2. And I'm also going to put another 3 dots signifying the numbers that are greater than 2, and I'm just going to squish them down at that little tiny space. The next smallest set of numbers would be, the whole numbers. And the way we describe this is that we're going to take 0 and all the positive numbers. So like 1, 2, 3, 4, 5, and so on. And whole starts with W. So mathematicians decided that our symbol for whole numbers is going to be a double scripted W. So we're going to have W, and we're just going to add a line somewhere, and that signifies that it's a set of whole numbers. And again, whole numbers look like 0, 1, 2, 3, and it goes on forever. Other than that, we have the natural numbers. So the way that the natural numbers came about, we started counting things. And we had an idea to say, okay, this is 1. That's 2. That's 3. So we describe the natural numbers as the whole numbers, except we remove 0. So it's just going to be the positive whole numbers other than 0. And our symbol for natural numbers, natural starts with N, so we can probably use N. So we're going to use a double scripted N to signify natural numbers. And again, those are like the counting numbers. So we can have 1, 2, 3, 4, and so on. Again, those 3 dots signify everything greater than 4. So it's going to be all those numbers squeezed into a tiny region, so I don't have to write them all out. Now, we're going to get to a section here where I'm going to ask you to name all of the possible sets that a certain number can be inside. And I'm going to go through all of these with you, so all 12 of them. And then we're going to have another bit of notes, And then I'm going to give you basically the same thing to practice on your own. So our number's 30. It counts. So it's a counting number because you can look and you can have 30 things. We're going to say that we're definitely going to be in the natural numbers. And I'm not really worried about writing the scripts or anything. I just want the letter that describes the set. So for naturals, you can put N, for wholes, W, integers, Z, rationals, Q, irrationals, I, and real numbers, R. So 30 exists in natural numbers. Well, since it exists in the natural numbers, we know that it's also a whole number. It's also an integer. It's also rational, and it's also real. So 30 belongs to 5 different groups. Okay? Moving on to number 2, we have negative 11. Well, is it a counting number or a natural number? No, because you can't really picture negative 11 things. Is it a whole number? Well, no, because it's not a counting number and it's not 0. Is it an integer? Yes, because integers are the negative whole numbers, 0, and the positive whole numbers. So that means that it belongs to the integers, which is Z, the rational numbers, and the real numbers. Moving on to number 3, we have 5 and 4/7. Is that a whole number? No. So we can throw out natural numbers, whole numbers, and integers right off the bat. So that leaves us with rational and real numbers. If it's a fraction, it's rational. So since it's a fraction, we know that it's going to be rational. And if it's rational, then we know that's going to be real. So number 3 only has 2 sets, and it's rational and real. Moving on to number 4, we have the square root of 21. If you were to put that into a calculator, you would get a never-ending decimal. And what group does that mean that it's a part of? Well, that would mean that it's part of I, or the irrational numbers. So we can say that I, or that the square root of 21 is a part of I. And if it's a part of the irrationals, we can say that it's a part of the real numbers. So this one also has 2 sets, I and R. Number 5, 0. So you can picture 0 things, so that's okay. But we have a different idea between natural and wholes. So a natural number is the counting numbers, but you don't start off counting with 0. We start with 1. So I know that that's not in the natural numbers. But the whole numbers, well, it's the natural numbers plus 0. So it's going to be there. So we can start off with having 0 in the whole numbers. If it's in the whole numbers, then it's in the integers. If it's in the integers, it's in the rationals. And if it's in the rationals, it's in the reals. So we have 4 different groups that's a part of: the whole numbers, the integers, the rationals, and the reals. Number 6, we have negative square root of 9. Well, square root of 9 is a real number. Like, it comes out to be a whole number. It's 3. And if we have negative 3, that means that it's not a counting number because we can't really imagine negative 3 things. It's not a whole number because it's not 0, but it is an integer because we have the negative counting numbers, 0, and the positive counting numbers. So the first set that number 6 can go into is going to be the integers. So we have Z. And if it's in the integers, it's in the rationals. And if it's in the rationals, it's in the reals. So we have 3 different sets that number can be a part of. Next, we have 6/3. Well, 6/3 can be reduced to just 2. And you can picture two different things. So I know that's in the natural numbers. Since it's in the natural numbers, it's also in the whole numbers. and the integers, and the rationals, and the reals. Moving on to number 8, pi. Pi was one of our examples for irrational numbers, so we know that it's irrational. So that means that it's part of I and R. Number 9, we have 5.3 with a line over it. That line means that it keeps repeating, so it's actually 5.3333333 for infinity. What quality does that give us? Well, we said that irrationals have decimals that never end and have no repeating pattern. So that throws that out because the 3 repeats. Well, a rational number or have decimals that end and have a repeated pattern. So it follows under both of these. So I would say, or not both of these, but it falls over under the rational numbers. So number 9, we have rational, and if it's a part of the irrationals, then it's part of the reals. Now we're going to start getting into a little bit trickier ones. So if we look at number 10, we have the square root of 144 divided by -3. Well, that can simplify a little bit because the square root of 144 is a number, a whole number. So we can say that the square root of 144 is 12, and we're dividing that by -3. Well, 12 divided by -3 gives us -4, and now we just have to figure out where -4 goes. So since it's negative, we know that it's not going to be a part of the natural numbers or the whole numbers, and it's going to be a part of the integers. Since it's a negative whole number, we know it's going to be a part of the integers. So we're going to say the integers, and if it's in the integers, it's in the rationals, and if it's in the rationals, it's in the reals. Number 11, we have -2.875. The decimal ends, so that means that it's going to be rational automatically. So since the number or the decimal ends and it's not repeating or anything else like that, we can just automatically assume that it's in the rationals. And if it's in the rationals, then of course it's going to be in the reals. Finally, number 12, we have the square root of 17 divided by the square root of 17. Well, that's just a fancy form of saying it's a fancy form of saying 2 over 2 or 3 over 3. In other words, this is just 1. 1 is a counting number because I can say that's one thing. 1 is also a whole number. It's also an integer. It's also a rational. It's also a real. So it's all of them except for irrational. So we have that 1 is a part of the natural, whole, integer, rational, and real. So I hope that helps with just classifying numbers. And I hope that you're able to grasp this really easily. This is just trying to understand exactly what the numbers actually are, and that they're in separate little groups, and I could almost call them families. So what we're going to do now is, if you flip the page, we're going to head over to the Organizing the Real Numbers page, and it looks like this. What we're going to do here is we're going to order the numbers. And the goal is to place the letter of each value. So in other words, if we look at A, it's 7. So we're going to take the letter A and we're going to place it in the smallest location. So 7. I can imagine 7 things, so I know it's going to be in the natural numbers. So what I'm going to do is I'm going to take A and I'm going to put it down in the natural numbers. And then just to help myself keep track, I'm going to mark through A, just so I don't use it again. Then I'm going to look at B. We have -36 over 12. Well, 36 over 12 can be reduced a little bit, and that reduces to 3. So we have negative 3. Since it's negative, we know that it's not going to be a part of the natural numbers or the whole numbers. And we know that the smallest group that's going to be assigned to is the integers. So since negative 36 over 12 changes into negative 3, we can take b and put it in the integers. And then we're going to mark through b. Next, c is negative square root of 36. The square root of 36 can be reduced to just 6. And since we have negative 6, it's not going to be in the naturals, and it's not going to be in the wholes. So that means that it's going to be in the integers. So we're going to have c in the integers as well, and we're just going to mark through that. Next, d is pi. For pi, it was our example on the last page of irrational numbers. So of course it's going to be irrational. So we're going to take the letter d, we're going to put it in the irrational bubble, and then we're going to mark through it. Next is e. We have 6.48. Since the decimal ends, we're able to say that it's most likely going to be a rational number. And it is a rational number. So that means that we're going to take the letter e and we're going to put it in the rational bubble. And then we're going to come over here and we're going to mark through e. Next is f. F is negative 2. Since it's negative, I know it's not going to be in the naturals, and I know it's not going to be in the whole. So that means that it has to go in the integers. So I'm going to put negative 2 in the integers. I'm going to put f in the integers, and then come over here and mark out f. Next we have g, which is negative square root of 10. If you put square root of 10 in your calculator, you're going to get a most likely a non-ending decimal. And because it's non-ending, I can say it's going to be an irrational number. So that means that g is going to go over here with the irrational numbers because the square root of 10 does not end. The decimal does not end. So I'm going to mark through g, and we're going to move on. H is 0. Where's the very first time that you start seeing 0? Well, you should be able to tell me that the whole numbers is the very first time that you see 0. So that means in the whole circle, we're going to put h, and we're going to come over here and mark it out. We have 3 more left. We're going to move on to I, which is 2 1/6. Since it's a fraction, we can go ahead and say that it's going to be rational because it's a ratio of 2 numbers. So we're going to put I for the rationals, and then we're going to go over here and we're going to mark it out. Next we have j. We have negative 0.7 with a line over it. Earlier I told you that the line over the number means that it just keeps repeating. So negative 0.7 with a line over it means negative 0.777777, and it goes on forever. And that property is one of the rational numbers. So that means that j is going to be a rational number. And then we come over here and we mark it out. Next for k, we need to reduce this just a little bit. So we have the square root of 4 over 81. Well, in order to reduce this, the square root is going to be applied to the top and it's going to be applied to the bottom. So we're going to have the square root of 4 over the square root of 81. Both of those are something called perfect squares, and they're able to come down to just a strict number. So the square root of 4 gives us 2, and the square root of 81 gives us 9. So now we have 2/9. 2/9 is a ratio of 2 numbers, so we know that it goes in the rational numbers instead of the irrational. And then since it doesn't give us a whole number, we know that it's not going to be an integer, a whole, or a natural. So that means it's just going to live in the rational numbers. So Square root of 4 over 81 changed into 2 ninths. So that means that k is going to be rational. We're going to come over here and mark it out. And we're done with this section. If you have any questions about this, let me know. And we're going to move on to the final section of our notes. So with this section, we're having some multiple choice questions and some fill in the blank. So number 1 says, which expression does not name an integer? Well, what you need to do is check each letter and tell me if it's an integer. So A, negative 15. That's an integer. C, 0. That's an integer. D, 12 over 6. Well, that reduces to 2, and 2 is an integer. B, 6 over 14. If you put that into your calculator, you're going to get a decimal, so that means that it is not an integer. So that means our answer for number 1 is going to be B. Next, number 2, we have which expression represents an irrational number. So remember that an irrational number is one that has its decimals go on forever and does not repeat. So, A, we have 0.18 repeating. That repeats, so it automatically gets thrown out. 2/3. 2/3 is one of our examples on the front page of rational numbers, so we can throw it out. We have the square root of 3 minus the square root of 3. Well, that's the same thing as saying 1 minus 1. That gives us 0. And 0 is not irrational, so we can throw that out. Finally, we have the square root of 75. And well, the square root of 75, if you put it into your calculator, you're going to find that it has a decimal that does not repeat and keeps going on forever. So we're going to say that it is an irrational number, and that's going to be our answer. All right, this one should be really easy. Which number is not a whole number? Remember that the whole numbers are just the natural numbers, so the counting numbers, and then we add 0. So we can automatically throw C out because it's 0. We can throw out A because it's a counting number. And we just have to look at negative 10 and D. So let's look at D first. It's 18 divided by 3. 18 divided by 3 can be changed into positive 6. 6 is a counting number, so it is a whole number. So we can mark it out. And B is negative 10. Since it's negative, it's not going to be a whole number. So we can circle it as our final answer. Moving on to the final half of this section, we have which of the following is a true statement? A, negative 9 is a whole number. B, the square root of 25 is an irrational number. C, 0 is a natural number. Or D, 2/3 is a rational number. So what you have to do is go through each one and think about it. A, negative 9 is a whole number. Remember that the whole numbers are the counting numbers plus 0. And can you think of negative 9 things? No. So that means that it is not a counting number and it's not 0. So it means that it's not going to be a whole number. So A is a false statement. And remember, we're looking for the true statement. B, we have the square root of 25 is an irrational number. Well, if you use your calculator and you put in the square root of 25, you're going to find that it gives you 5. Is 5 an irrational number? Well, no. So this is also a false statement. Next we have C, which is 0 is a natural number. Is 0 a counting number? No, because we don't start off with counting 0 things, 1 thing, 2 things, 3 things, and so on. We start off with 1, 2, 3. So that means that it's not a natural number, and it's false. Well, D says that 2/3 is a rational number. If you remember on the front page, 2/3 was one of our examples of rational numbers. So D would in fact be true. Number 5, we have which of the following statements is false? We have A, which says all real numbers are rational numbers. B, every integer is a rational number. C, all natural numbers are integers. And D, every whole number is a real number. So before we answer this one, let's go back up to this picture right here. The reason that we have the circles like inside of each other is because if we look at the natural numbers, they exist inside the whole. We're adding something to the natural numbers to get the whole numbers. And then if we add something else to the whole numbers, we get the integers. And if we add ratios and stuff to the integers, we get the rational numbers. So these sets of numbers just keep growing with one another. So that means that the natural numbers are also rational. And the whole numbers are also integers. So in order to answer these questions, that's the kind of thinking that we have to have. So let's start looking at these. A, all real numbers are rational numbers. Well, are the reals inside of that bubble for rational numbers? Well, no, because real numbers are it's the big bubble, or the square, I would say. Not the square, the rectangle, I would say. So that means that's our false statement right off the bat. We don't even have to look at the other ones. We can say that A is our false statement, and therefore A is going to be our answer. If we look at 6, it wants us to give an example of a number that is a whole number, but not a natural number. Well, if we remember, the whole numbers are just the natural numbers plus 0. So the only option we're going to have is 0, because it's a whole, but it's not natural. And it's the only one. Next, we have 7. It says, give an example of a real number that is not rational. And my choice for this one is going to be pi, because it's a real number, but it's irrational. Because both irrational numbers and rational numbers are real numbers. And I'm going to put a little asterisk around here. And I'm going to say that your answers may vary. And what I want you to do is, instead of choosing pi, I want you to go through and try and think of a different number that would be irrational. Finally, we have give an example of a rational number that is not an integer. So the number that I'm going to choose this time is 1/3, or 0.3 repeating. And again, this one is going to have answers may vary. And I want you to do the same thing. Instead of just writing down 1/3 or 0.3 repeating, I want you to think about a different rational number that is not an integer. So you're going to be looking for a fraction that you think is a rational number. So thank you all for paying attention to this video. Tomorrow, you're going to be getting a worksheet on classifying real numbers and doing basically the things that we did today, except for your own independent practice. And that is going to be due on Friday, September 18th of 2020. And it's going to be due by midnight, so you're going to have to turn it in by 11:59. I want to remind you that you do have to turn in work, and in order to turn it in, I need a picture taken or the file uploaded or something to Google Classroom using the correct folder. And if you do anything in this class, I need you to make sure that once you complete something, you go to Google Classroom and you turn it in, even if there's not anything to turn in. It lets me know that you're still doing stuff. Other than that, that's all I have for today. So tomorrow, you're going to be working on the classifying real numbers worksheet. Friday, you're going to have time to continue working on both worksheets from this week. And your goal is to turn them in by 11:59. Then on Monday, Tuesday, and Wednesday, we're going to be working on the benchmark of the year. So what I need from you is your patience and I will try and have that ready for you. It might get pushed back, but I'm not completely sure. But I hope that you have a wonderful rest of your day, and I look forward to seeing you soon.